Hopefully at this stage, you're reasonably comfortable with the idea of characterizing multivariate distributions through joint distributions and also perhaps through conditional distributions where I have some information about the values of one or more variables and I can characterize my uncertainty in the other variables conditional on what I know. There is another case, which is where I want the marginal distribution, where I want to know to characterize my uncertainty in one of the variables. I don't really care that much about the other. So we take this from the simplest case, which is discrete and with only two variables. The joint probability mass function of x and y. If I just wanted to know what's the chance that x took a value m, well, I'd just add up all of the ways that x equals m. So I'd add up all of the pairs where xy equals mn, just picking out the ones where x equals m and summing over all of those for all possible values of y. So this doesn't require any knowledge of what the other variable is. It doesn't require any knowledge of y. In fact, quite the opposite. It just says, I don't really care about that. I'll just sort of effectively average over my uncertainty in that variable. So what it does mean is that the marginal distribution can't have lower variance than the conditional distribution, because saying I don't care about y, I'm just going to wrap up all of my uncertainties in what y might be in my uncertainty about x, is inherently more variable than saying I know that y equals 3. How variable is my x? Now, you can see that from the law of total variance, where we've got the variance of y is the expected conditional variance of y given x plus the variance of the expectation of y given x. And of course, if I know x, then obviously that would simplify considerably. If you've seen the previous two videos, you'll recognize this example. And this was just saying that if we flipped 3 fair coins and counted x to be the number of tails on the first 2 flips and y to be the number of tails on the first 3 flips, then obviously we got x and y being, well, very dependent on each other, and we worked out the joint distribution as this. Now, if I want to visualize what a marginal distribution is, that's just effectively collapsing and summing over the variable that I'm not interested in. So if I want to work out the marginal distribution of y, that's just saying how much of this joint probability distribution is associated with y being 0, how much associated with y being 1, how much associated with y being 2, how much associated with y being 3, where I do not care what the associated x was that produced that. So you can visualize this by kind of crushing the x dimension inwards and stacking up. So obviously the N2 blocks, the one associated with y equals 0 and y being 3, only have one block of probability mass in, whereas the other two, the squared, sort of checker box one, I've got to sort of stack the blue block and the taller red block, and the solid shaded one associated with y being 2, I've got to stack the solid red block with the shorter black block. And there's no normalization required here because all of the probability mass in the joint distribution should be in there somewhere. So you can see I've got heights of 0.125, 0.375, 0.375 and 0.125, which you actually may well recognize as being the distribution of a binomial variable with parameters 3 and 0.5, which is what I would expect for 3 flips of a fair coin. So I can sense check and have confidence in my answer.